fellow National 5 chemists. Today we are moving on to our last little bit of work that we need to cover. And once we've covered it, we'll have done everything in the National 5 course. So we're nearly there. The end is in sight. We're going to just do a couple of little lessons now on nuclear chemistry. And there's 3 lessons that we're going to want to look to cover. The first one, which is this lesson, we're going to want to look at the different types of nuclear radiation. We're going to want to look then in a separate video about incorporating nuclear radiation into balanced chemical equations, and then in the final video we'll look at half-life and some half-life calculations. So 3 kind of things to get through, but back to what we're doing today. We're wanting to introduce our 3 nuclear particles, nuclear types of nuclear radiation that we are going to want to know for our National 5 chemistry course. Now, before we dive into the actual lesson as such, let's have a look at this little video clip that will give us some background information, a little bit of context before we explore these different types of radiation.
We are exposed to radiation every day, from our mobile phones to cosmic radiation from the sun. But what is radiation?
Radiation is just energy travelling through space. So the heat coming out of your hairdryer, you could say, is radiation. The trouble is that what most people mean when they say radiation is radioactivity, and that's different.
Radioactivity is the nuclear decay of unstable elements. In order to reach stability, atoms within these elements emit excess energy or mass, nuclear radiation. When nuclear radiation hits atoms or molecules, it can change them into charged particles called ions by causing them to lose electrons. This is ionization and can be detected using a Geiger counter. When radioactive atoms in elements like uranium decay, they can release 3 types of nuclear radiation: alpha, beta, and gamma. Some atoms emit alpha particles, composed of 2 neutrons and 2 protons. They can only travel a short distance through air and can be stopped with just a piece of paper. Beta decay releases fast-moving electrons, beta particles. They travel further through air and even through paper, but can be stopped by something thicker than paper, like this perspex. Because alpha and beta radiation are particles, we call them particulate radiation. Gamma rays are a type of electromagnetic radiation. Gamma rays are extremely penetrating. In fact, several centimeters of lead or a few meters of concrete are required to shield from gamma rays. The high penetration of gamma rays does not necessarily make gamma radiation the most dangerous.
There is a difference between the penetration of radioactivity and the damage that it does when it's there. The gamma radiation will penetrate a long way, but alpha radiation, when it's in the body, will produce a lot of damage to the genetic material.
Radiation can be extremely useful, for example in medical applications. But it's important to understand the risks involved with radioactive substances.
Now, as we saw in that little video, there are 3 different types of radiation. The first type of radiation mentioned there, and the first type that we'll talk about, is alpha particle radiation. And when we're talking about radiation in chemistry, as it said in that little clip there, strictly speaking, this would be radioactive decay. There's lots more than just 3 types of radiation, but when we're dealing with it in National 5, instead of having to say radioactive decay, we're just going to shorten it to say radiation, and there's only 3 different types of kind of chemical radiation that we are interested in: alpha particle, then beta particle, and finally gamma wave radiation. So there's our three different types. We'll go through each one of them now and we'll sort out the things that we need to know for each one, such as the symbols, such as their charges, masses, nuclide notation, etc. So here's our first type of radiation, an alpha particle radiation. An alpha particle is the largest of the three types of radiation, and it contains 2 protons and 2 neutrons. So that's what an alpha particle is. It's got 2 neutrons and 2 protons. And we can think of it as a helium nucleus. And we can write out alpha particle radiation in nuclide notation by using the symbol for helium, because essentially it's just a helium that's lost its electrons. It's just a helium nucleus. It has 2 protons, so the atomic number for helium is 2. Since it has 2 protons, and its mass number, well, 2 plus 2 is 4, so its mass number is 4. And we can also put a charge on this as well, being 2 positive, because it's got 2 positive protons and no electrons to balance those positive charges out. So that's one way that we can write alpha particle radiation, and definitely one to remember. Additionally, the symbol for alpha particle radiation is this Greek letter alpha, which kind of looks a little bit like an A with an extended top part, if you will. And again, you might see this notation for alpha particle, where instead of they've put the symbol for helium, they've just used the symbol for an alpha particle instead. So both of those are very important to remember, and it helps us remember what an alpha particle actually is. If we think about the mass number and the atomic number, 2 protons, mass number is 4, so there must be 2 neutrons as well. 2 plus 2 is 4, and it's got a positive charge because there's no electrons. And just like all of our types of radiation that we'll look at here, this is alpha particle radiation is created within the nucleus of an unstable element. And so when we get to kind of the latter part of the periodic table, we've got really, really big elements with 90 plus protons and neutrons. They can have isotopes that aren't very stable. And one way that they can stabilize is they can react, like we've been talking about for years now, to form a nice stable compound, or they can undergo, if they're radioactive, radioactive decay, and they can emit and release alpha particle radiation, beta particle radiation, or gamma rays. And it's just one way that some elements can try and stabilize themselves, by throwing out some excess protons and neutrons. And if they throw out 2 protons and 2 neutrons together in a little particle, then it's just an alpha particle. And if we had to, I suppose, imagine what an alpha particle looks like, if we can kind of zoom in under a very powerful microscope, we've got our 2 positive protons and our 2 neutral neutrons, and they're just kind of stuck together in a little particle. And that's it. That's all an alpha particle is. 2 protons, 2 neutrons, and these are the ways that we would want to be able to just annotate that in chemistry. Our next type of radiation then, beta particle radiation, a much smaller particle, much smaller. All a beta particle is just a high energy, fast moving electron. So it's a quick electron that's been chucked out of the nucleus, and you might be confused by that, but it'll make sense in just a second. An electron that's been chucked out of the nucleus of an atom. And just like we talked about with our alpha particle radiation, there's a couple of ways that we need to be able to annotate beta particle radiation. The beta particle can be symbolized by the symbol beta, which is just a capital B with a tail. It doesn't have to be that long. It's probably a little bit long there, but it's fine. And since it's an electron, we can also annotate it as E for electron. And if we're concerned about the mass number and the atomic number, which we are, we can put in the nuclide notation of it has a mass of 1, because electrons don't have any mass, and its atomic number is a little bit strange, but its atomic number is -1, and that will make sense in just a little bit. So it can either be a capital B with a little tail, with a 0 at the top, and a -1 for the atomic number, or a small case e, because it's just an electron. That's all beta particle radiation is, just an electron. And we know electrons are negatively charged as well, so this would have a negative charge on its particle. So mass number of 0, atomic number of -1, and a charge of -1. So we might be confused by a couple of things there. Why is the atomic number -1? Or why is this fast-moving electron produced from the nucleus of the atom? Well, we need to think about how beta particles are formed. They're formed because a neutron in the nucleus has broken down to form a proton. And in that transformation, in that breakdown from a neutron changing into a proton, a fast, high energy electron is produced. So if I change a neutron into a proton, that's fine, but at the same time, an electron is just fired out extremely fast out of the atom into the atmosphere, into the surrounding environment. And that is beta particle radiation. Okay, so that explains where the beta particle comes from, but doesn't quite explain this -1 just yet. So let's think more about writing this transformation from a neutron into a proton in more of a typical chemical reaction. We're taking a neutron and we're changing it into a proton, and at the same time, as we said, we have got an electron being produced. The mass number for a neutron is 1. Neutrons have a mass number of 1, and they would have an atomic number of 0, because remember the atomic number is a number of protons. Neutron doesn't have any, isn't a proton, so it's just 0. But it has a mass of 1. It can break down though to change into a proton. A proton would have an atomic number of 1, because that's how many protons there are, and it would have a mass number of 1 because protons have a mass of 1. We've already talked about electrons having no mass. They don't have a mass at all, so it's a mass of 0. And now here's where the -1 part comes in. This equation needs to be balanced, both in terms of the mass number and the atomic number. And we'll do this quite a lot in the next video when we look at a lot more detail at equations like this, a little bit more complicated ones, but essentially doing the exact same thing. We're going to look at on the left-hand side, the total mass number. So on my left-hand side, I have a total mass of 1. That's easy. My atomic number on the left-hand side of the arrow is 0. So that means what I have on the right-hand side must also match this. I need to have a mass of 1, which I do. 1 plus 0 is 1, okay. But I also need to have an atomic number the same on the left-hand side, same as 0. Currently the atomic number is 1. Okay, that doesn't fit in. So therefore, we can think of the electron as having a -1 atomic number to balance out these atomic numbers, to make sure that whenever we have a chemical equation, everything is balanced. And so now the atomic number is 0, and this equation just shows the formation of specifically what we're interested in, beta particle radiation. It's this high energy, fast moving electron that is important to us. Now, as I said, don't worry too much about that mass number, atomic number part just now. If you get it, perfect. If you don't, we're going to do a lot more of it in the next video. And finally, not much really to say about gamma rays. We don't talk about them too much in terms of chemical equations and in terms of our National 5 course, but we do need to be aware of them, and we do need to know a little bit about them, but not nearly as much as our alpha and beta particle. Gamma rays can be thought of being like a wave. They're not actually a particle. They're just a form of energy. There's no protons and neutrons and electrons in a gamma ray. It's just energy, pure energy. It doesn't have a mass. And those are the kind of key points that we need to know about gamma rays. We'll talk a little bit more about its properties in just a second as well. But I suppose one other thing to note would be its symbol. To donate a gamma ray, which is kind of a little bit like a fancy Y, I suppose. That's not the best drawing in the world. Maybe something more like this. But a gamma ray is the Greek letter for gamma, is this Y symbol. And that donates the gamma ray. And that's pretty much all we need to know for it. So we've got our three different types of radiation, our alpha, our beta, and our gamma. Remember, our alpha particle is this kind of large, chunky particle. It's a helium nucleus, 2 protons, 2 neutrons. Our beta particle, much smaller, high energy, fast moving electron created by the breakdown of a neutron into a proton. And then our gamma radiation is a wave, it's not a particle, and that's really the end of the story for gamma. All of these sources of radioactivity are all emitted from the nucleus of a radioactive element. And we can look at the properties of this radiation as well, and we can look at how it would interact with something like an electrical field. So if I take some alpha particle, beta particle, and gamma ray radiation, and fire it through this electrical field where one side is positive and one side is negative, then it should interact with the different particles based upon their properties. So as we've talked about, alpha particle radiation is a helium nucleus. It has a mass number of 4, atomic number of 2, and a charge of 2+. So if I fire some alpha particle radiation towards this electric field, the second it gets the electric field, it's going to interact. There's a positive side and a negative side. Alpha particle radiation is positive. It is going to be repelled by the positive charge, doesn't like it, and it's going to be attracted by the opposite charge because opposites attract. So that is going to start to move towards the negative side, and that would be our alpha particle radiation. Then we can look at the next one, our beta particle radiation, which is this fast moving high energy electron. Again, it's just going to travel in a straight line up until it hits the electric field. And if we remember, our beta particle radiation is an electron. It has a mass of 0, an atomic number of -1, and a charge of -1. So that is negatively charged. It's an electron. It's going to be repelled by the negative side and attracted by the oppositely charged positive side, and that will start to go out like this. And there is our beta particle radiation. And lastly, our gamma particle radiation. Excuse me, that's not correct. Gamma is not a particle. Our gamma ray radiation, you can think of it as a wave. There's no mass to it, there's no charge to it, it will not interact with our electrical field. It doesn't care about positives and negatives because it itself is not positive or negative, so it just goes straight through unaffected. And our last little thing to look at here is the penetrating power of our different types of radiation. Alpha particle, by far the biggest. We've got our 2 protons, 2 neutrons. If I fire that at a single sheet of paper, that paper is more than enough to stop the alpha particle radiation. The alpha particle radiation is just too big to get through the paper. It can't penetrate through the paper. Next up is our high energy fast moving electron, which is our beta particle radiation. That is definitely small enough to fit through the paper, slide straight through the paper, but is stopped by a couple of centimeters of aluminium foil. Can't get through the aluminium foil. It's too big to get through the aluminium foil. And lastly, our gamma wave radiation. Well, our gamma wave radiation goes straight through the paper because it's tiny, it has no mass whatsoever, the gamma wave radiation. It goes straight through the aluminium as well, no problem, and goes the majority of the way through lead, but we'd probably need about 3-4 feet of lead or concrete to stop the gamma radiation. That by far has the best penetrative power. Beta particle has got okay penetrative power, but alpha particle is stopped by just something like a thin sheet of paper. And if we look at this little past paper question, here's a question just based on it, where you've got some information, some radioactive sources, and they're being fired at these different materials. Quite simply, you have to identify the type of radiation from each source. So the first source is going through paper, it's going through aluminium, and is being stopped by some lead. Well, this must be our gamma particle radiation. That has the best penetrative powers. Second one, it's getting stopped by paper. This must be the biggest particle that we have. This must be our alpha particle radiation. And the third one, well, we've by process of elimination figured out that this must be beta particle, and we can also see by the diagram it passes through the paper but it's stopped by our aluminium. Okay guys, now that's everything that we need to know for our 3 different types of radiation. In the next video we will look at kind of integrating these types of radiation into balanced chemical equations.